All right, we are back. My name is Seth. Tomas is not here, but that dude is a machine. He just went through, I don't know, 50 million sessions. Is that right? Okay. So I have here a really good guest. Faisal, tell us a little bit about who you are and what you do, my friend.
Hi, I'm Faisal. I'm basically work in the automotive industry in the Detroit. I've been working there for a long time. I'm also pursuing postgraduate studies, so doing a PhD in computer science at the local university.
Fantastic. And so where are you based out of, first of all? Where are you at right now?
I'm in Detroit right now. Yes.
Fantastic. So tell us, why don't you get started with your talk and tell us what's going on? I'm going to get off to the side. That way you can sort of instruct us on some cool stuff.
Okay. Okay, very good. So welcome everyone to the F-sharp conference. So I'm going to talk about this idea of functional state machines. And this is really a very interesting application of functional programming and use of F-sharp. And then we can apply it to in a lot of different places. And one of the ones is going to be, for example, gesture recognition on a smartwatch. Hey, sorry, I didn't quite catch that. Okay. Okay, very good. So I'm going to start my presentation. So let's see, I'm going to switch over to a laser pointer because I like that. Okay, so this talk is about functional state machines. I'll give you some background and motivation. How and why did I come up with this idea? And then we'll talk about, how do you put basically take a look at Android wearable application. What does it take to put that together? So we'll take a look at that. And then at the same time, right after that, we'll talk about this idea of functional state machines. How do you then make them handle more complex pattern? And I'll just briefly touch upon, how you can then sort of use machine learning to optimize these functional state machines to recognize complex patterns. Okay, so now out in the industry today, there are three sort of very distinct trends that are going on. So the first trend actually the screen is not showing. Can you see my latest screen? Okay. Okay. So so then you have, for example, you have the automotive systems. They're becoming more and more complex. So the OEMs or automakers are looking to reduce driver distraction. So they've started using speech recognition, but that has its own issues. And now you're starting to see gesture control. BMW has a sophisticated system that uses cameras in the roof to track your hand movements. Now, if you look at the smartphone makers such as Google and Apple, they're trying to kind of take over the dash by products such as Android Auto and Apple Car, and then there's this whole wearable computing revolution happening. And so, a natural question you can ask yourself is it feasible to use something like an off-the-shelf wearable device and use that for gesture control of the automotive HMI, maybe through products such as Android Auto or Apple Car? And so this is the question I set out to answer. I did some research and an implementation, and this talk is really about the learnings from that experience. So for my implementation, I created an app that runs on a Android Wear smartwatch. Of course, it's written in F-sharp using the Xamarin toolkit. Then this app can recognize simple gestures. It has, this is gesture vocabulary down at the bottom left. So you twist this watch, and then it goes into gesture recognition mode, and then you can do gestures such as tap, swipe, left, right, or you can escape out and go back to, non-gesture recognition mode. And then these gestures are then used to drive a sort of a mock menu hierarchy, so you can call somebody, send text, and so forth. So that was the experiment that I did. And I discovered this idea of functional state machines while working on that, and that's what I'm sharing today. So Now, if you look at the gesture recognition, really, it's just recognizing patterns, but in noisy data, or you're recognizing stochastic patterns or probabilistic patterns. There's many sources of noise. The sensors are inherently noisy. On a watch, you have the accelerometer, the gyro, and the magnetometer. And also, human limb movements, they're not precise from, instant to instance. In our case, with this, the vehicle motion that's in the mix. So it's fairly a complicated problem. Now, there are many techniques out there that you can use to address this problem. So hidden Markov models is the most commonly used ones, but there are many others like neural nets, or you can also use support vector machines. But finite state machines are also used. And the thing about finite state machines is that they're computationally efficient, right? They're suitable for these low power devices, where you're concerned about the battery life, of course. But then they also have some problems. So one of the things is that if you have a complex pattern, then you run into this state space explosion problem. And then the textbook variety of finite state machines don't really tell you how to handle probabilistic or stochastic patterns. So this talk is really how can we address some of these minus points and while taking advantage of the the computational efficiency. Okay, so I'm going to switch gears a bit. I'm going to then now talk about an Android application, and we know what makes a wearable application tick. So we're first going to look at a very basic Android application and see what does that look like, and then we'll look at something more specific to wearable applications. I'm going to switch over to Xamarin Studio. Okay, here's Xamarin Studio. This is a IDE from the company Xamarin, which now, of course, is owned by Microsoft, so that's great news. And one thing about Xamarin is that they have done excellent work in making sure that F# is a first-class citizen on Xamarin Studio. So I'm going to start and just create a simple app just using the default template. I'm going to create a new solution and pick this Android app, and I can choose C# or F#. So I'm going to choose F# here. Click next and just give it some name and take the defaults. And in a few seconds, you should start to see a brand new app created. So while it's working, I'm going to talk a little bit about, what I'll do is I'll just run this app and show you what this app does so that you get a sense of what's going on, and then we'll just sort of dig into it and look into it. So, okay, so now that the app is running, app has been created. Unfortunately, I'm having some issues with my licensing, but it looks like everything is good now. Okay. Okay, so I'm not going to run this app now. It's going to build and deploy this app to this emulator that's running over here. And while it's building, I'll briefly talk about what's in the app. So an Android app, it has a fairly sort of elaborate structure. It has many folders. Eventually, it gets come into a zip files, but that gets signed and then that gets deployed. But it has a lot of structure that you have to sort of know about. So there's this resources folder that's kind of important because there's lots of things in there that you have to sometimes configure. And one of the important things is the layout. So the screens that you have in your Android application go into this layout folder, and they're essentially XML files. Okay, so it looks like our app was deployed and it's now running. And I'm just going to click this button. It's a very simple app. Just count clicks. It's one of the default templates, and then I'll explain how is it put together a little bit. So in Android, you have this idea of activities. Activities are like controllers. They sort of is a class that is controlling a particular interaction with the user. It also shows the user the screen on the phone and the controls on it, and then and sort of also handles when the user interacts with that screen. So in this case, we are implementing something called main activity. It inherits from the Android class. where you know, this main launcher actually means that this is the when the application starts up, this is the screen that will be shown. And typically in Android, you basically override this method, this onCreate method, and then one of the first things you do is you set the screen, right? So the screen, as I told you before, is this XML file over here. Now, Xamarin has kind of improved upon that they have Xamarin forms where you can use data binding. But if you're using sort of plain old Android, you kind of do these things, you know, manually. So now, you know, so we've set the view, and then after that, what you do is you typically go and look up all of the controls on your view using this find view by ID. So here we have a button that we have on that screen, and then you can wire up your interaction. So for example, you know, if I set a breakpoint here, and then go to my emulator, and then click this button. Just give me 1 second, my mouse is a little slow. Then it'll stop at this point, and then I can go in and inspect the variables and so forth. So all in all, Xamarin has done an excellent job to make sure that the F# is handled well, you know, on their platform. Okay, so we just quickly looked at what a basic Android application looks like. One of the important things about the Android application is this manifest file. I'm going to point that out because this is something that is important when you're building a wearable application also. So this contains the metadata about the application, like the version and the package names and what the permission the app has. It essentially is an XML file, but Xamarin and has this editor that you can also use. Now let's take a look at what does a wearable application look like. So essentially, a wearable application is an Android application. So you can see over here is that in this Xamarin solution, I have two projects under that solution. One is the host application, and the second one is the wearable application. So a wearable application is essentially an Android application, but it references different libraries, and it has some restrictions. And the UI mechanism for this is the UI controls are very different, right? I mean, the way you use the UI is still the same, but the controls that are available to you are different. Although you can use some of the phone controls there as well, but they don't really render well. Okay, so what happens is that you build two applications. One is the host application, and the second one is the wearable application. Then you take the wearable application, you embed that in the host application, and then when you deploy the host application to the phone, and if the phone is paired with a smartwatch, it will actually go in and take this inner application and deploy it to the watch. Right? That's how this process kind of works. Okay, so now, one thing that is important to note is that if you're building a wearable application, you have to worry about certain things lining up correctly. So here I'm showing you two manifest files. We just looked at the manifest file. So this is the host manifest file. There's the wear manifest file. The first thing you have to make sure is that the host version, the version name and the package name in both have to be exactly the same. If you don't do that, then basically your application doesn't get deployed, and it's very hard to debug. The Android tooling kind of does that automatically, but when I was using Xamarin, I had to sort of figure that out on my own. So this is something that you should be aware of. The second thing is that if you have permissions in your wearable applications, for example, you're going to use sensors in your wearable application, make sure that your host application also has the same permissions. So the wearable must have a subset of permissions. Otherwise, it actually doesn't work. And again, it's hard to debug. Okay, and the next thing is, how do you actually package the wearable application into the host application? So we're going to take a look at that. So the one thing to note is that you start off with the host manifest file, and there's this special tag. It may be different now, but you set the value of this tag in the manifest to an XML file, And this is the XML file that you've included in the XML folder under resources. So this is resources, and under resources you have this folder called raw and XML, and an XML file is there. The XML file actually points to your variable application, which is this .apk file under the raw folder. Right, so this, if you, so you have to do all these things and make sure everything lines up correctly, the package names, version names, etc., and then make sure they all line up correctly. Otherwise, your application doesn't get deployed. Okay, so I'm going to quickly now show you actual running wearable application. So let me, sorry. Where's that thing? So this is an emulator that's running. That's running it's for a wearable thing. And here's a wearable application. It's one of my gesture recognition applications that I'm just going to just run it. I'm not going to explain too much about it. There's a lot of code there, and you can see that, this shows up on the wearable. And again, I can, for example, debug this quite easily. So while you're debugging, you can just deploy it directly to a wearable, right, in the debugging mode. But when you actually package it, then you put it in the host file. So here is one of the classes that gets executed when I switch the service on. So I'm just going to show you, for example, what happens that you can do the same kind of debugging here. If I turn this button on, this code got executed, and now I hit this breakpoint, so I can now debug my application quite easily. So that just wanted to give you a feel for that. Okay, so now I'm going to explain a little bit about communication mechanisms. So when you have a wearable application, you actually have two applications, one on the host end, one on the wearable end. And two, quite often the two have to talk to each other. For example, the wearable may not have an internet connection, so it may need to get that from the host application. So Google has created this high-level API called GSM that runs on top of Bluetooth. What the API does is allows you to send messages back and forth. So these are small, they can carry a small amount of data. I think they're not guaranteed to be reliable, but that's what you often use for simple communication. And then you have this other mechanism where you have data that's synchronized. So this is used for larger items like files or images. So when you have a data, you can create it on one side, and then it'll be replicated to the other side eventually, right? It's consistent. What you also have to do is implement this service has to exist on both places if you want to, send and receive, not send but receive messages from one device to another. Okay, so I don't have time to go into the details, but at the end of this talk, I'll give you a reference to the code that's out there on GitHub. You can go in and take a look at it and understand it in detail. So now we're going to switch gears a little bit and talk about this idea of functional state machines. So first of all, almost everybody knows what a finite state machine is. That's computer science 101. But just to recap, let's say you want to recognize a pattern. So you have a sequence of characters, and you want to recognize this pattern 3 A's followed by a B, exactly 3 A's followed by a B. You might build a state machine that looks like this. Here you're in the start state. If you don't see an A, you just transition back. If you see an A, you go to this A1 state. If you see another A, you go to A2 and so forth. Now, obviously, I'm not showing all of the transition like exception handling, but essentially it gives you an idea, what's happening in a finite state machine to recognize patterns. It turns out that there's a very sort of natural transformation from this graphical representation to a functional code in terms of finite state machines. So states just become functions, and event handling becomes pattern matching on functions, and transitioning just means returning another function. So we're going to take a look at the same state machine, but now in code. So on the left is the graphical version, on the right is the F# code version. Just let me explain a few things here. So one of the things is that anything that's in bold red, like the start, is actually a function and a function state, if you will. So start corresponds to this state over here, and you can see the other states. Now, the body of this function, so this function keyword in F# tells that the body is basically pattern match clauses. So the body of this function is pattern match clauses. So this is one clause, and here you're matching the character A, and then when that matches successfully, you're doing this action. Now, what is important is that there is an implicit argument to start. So the start takes this argument, which is of type character, and then returns essentially the next state if the match is successful, which is this A1 kind of function over here. But we're returning this function in this M type. So this is a recursive type that you need for the types to line up correctly. So this is all there is to build a sort of a state machine in functional code. And what I'm going to do now is actually show some of this actually running. So let's switch over to Visual Studio. I actually just show this code how that runs. So now, in practice, you need a little bit more. So what we have done is we've taken our M type and we've extended it with another type parameter. So now, as before, we have our type signature for the state function, but an M now packages two things, like the next state and also some kind of output. We need this output. So we need the next state, but we also need this output to sort of keep track of what's going on and whether we have found a pattern or what we should do. So in our case, we're going to take this this type here and use that as the second type argument. So this type essentially is telling us what's going on in terms of our pattern matching. Keep going means, yeah, we're on track, keep going. Found it, yeah, we found the pattern, or no, we're in a state where we're never going to find a pattern, so let's abort. Right, so now as before, this is my state machine, this is my start function, which is looking for this character A, but now when we return this M with next state plus this tag, so in this case, if we see an A, that means keep going, so we're on track. If you're in the start state, if we see something else, we go back to the start state. So you return the start state, but we also keep going. Now, if you're in this A1 state and you see an A, that's good. Yeah, keep going and switch to A2 state. But anything else means, okay, we're not going to see this, the pattern is not there, so let's abort. And we output this abort symbol and go to this aborted state. And if you chase through this, if you find the pattern, you go to this done state and the output is founded, right? Okay, so let's just quickly run it and see what happens. I'm going to take this code and compile it in F# interactive. Okay, so that got compiled, and now here's my test data. What I've done is taken a string and just converted it into characters. So that's my input data, and inside this string is this pattern that I want to match, 3 A's followed by a B. So let me compile that. And then what I've done here is I've taken this sequence of characters and I've created sort of another sequence of sliding windows of size 4 on top of that, right? So because, I want to be able to match this, and then I want to be able to match this and so forth, right? So now my data is now ready. I'm going to then build something that actually runs the state machine. So I'm going to have a start state. So every time when I start detecting a pattern, I want to start with the start state. So I'll just have that, and this is my function that actually runs the state machine. So what it does is that it takes a sequence of characters, and then what it does is then it packages that sequence of characters with the start state, and then runs it to this sequence of fold function. And what the fold is doing is extracting the state information and actually the function that's in there. And then it takes the first character and essentially calls that function with the first character, right? And the result of this function call is another state. And so this fold will then take that whatever was the next state and feed it back into it. But then it will evaluate that against the next character in the sequence, right? So this is our function to run the state machines, and very simple way of doing it. Here, I've created a helper function to say if we have found our pattern or not. It just returns true if you found it, otherwise it's false. So let me just compile these two things. and compile this function. And now I'm actually ready to run it. So I have my segments, which are these sliding windows, and I'm going to say, okay, try and find this pattern, by running this detect composed with habit, right? So this is just a function composition operator. And if I run it, I should see, oops, it didn't work. Okay, so I think because I had already compiled it, so let me reset everything. Okay. Okay, so yeah, there was some previous code there. So now it found the pattern. So now if I mess up with this pattern, putting an X in there, and then run it again. Give me 1 second. And then it shouldn't find it, right? So execute and interactive, and no, it didn't find it, right? So this kind of gives you an idea how to model a pattern recognition kind of a system using state machines. Now, we can do actually much more. So let's make our problem a little bit more complex, right? So instead of now, let's say we want to recognize exactly 3 A's and 3 B's, but they can be in any order, right? So this could be one sequence, this could be another sequence. And one question you can ask yourself is that, well, this is a 6-character sequence. Can I have 6 states and wire up the transitions somehow to recognize patterns of this sequence? And the answer, unfortunately, is no. You can't really do that because you need an exponential number of states because you have to worry about the sequences. And if you start building a finite state machines for something like a pattern like this, it becomes unwieldy very quickly. And so now the question is, well, can we do better with this idea of functional state machines? So let's take a look at that. And so this is a functional state machine that can recognize 3 A's and 3 B's in any order. As you can see, sort of like it, the bold red words tell you that you only have 5 states, right? But we're cheating a little bit, So let me just run through this and explain what's going on. Okay, so this is our start function state. Assume it gets called with this character A, and then we switch to this FAB function state. But FAB looks different. It doesn't look like the start state where it takes this character and returns this, this M type. It takes 3 parameters. 2 are counts, and then this third parameter that's used in pattern matching. So what's going on here? This just doesn't look right. So what's happening is that this is not equivalent to a 1 state. We're using this function as a kind of a template for generating states. And then we're doing that through partial application. So in functional programming, if a function takes 2 arguments and you call that function with just the first argument, that's not an error. What you get back is a function that, as a new function that takes the second argument. So that's what's going on here, is that we are using this as like a template for generating states, and when we call this function with these 2 arguments bound to constants, we get back a function that matches our type signature for our state machine, and then that function will then accept a character as an argument and return the M type that we saw earlier, right? So what we have done essentially is kind of taken a bunch of states and sort of compressed them together into this single template state. So from a human, so the total number of states from a computer science perspective is still the same, right, in here, but we were able to organize that state space better because we have a more powerful way of building these pattern recognition systems. Okay, so let's walk through this. So let's say we return this FAB state with this bound to 1, this bound to 0, and now we see another A. Okay, so in this case, when it's called, this is bound to 1, this is bound to 0, because we've seen 1A so far. This condition will not succeed because count A plus 1 is not equal to 3. We are looking for 3 A's, but so far we have only seen 2, 1 before and 1 here. So then what will happen is it'll just drop down to the next pattern match clause, which has no condition, and we are seeing an A. And here we'll just return back to this FAB function state, but now we're incrementing this count. And so essentially what we're doing is we're looping into this kind of grouped state until we reach 3 for either A or B, and after that we switch to one of these states to count out the rest of the characters that we haven't seen yet. Okay, so but the key idea or the key insight is that once we start to model these pattern recognition systems with this idea of functional state machines, we can then make that much more powerful by using this partial application. We can organize our state space or kind of compress our state space, using this idea of partial application. Okay. Now, what I point out is that we were matching simple characters, but we can actually do pattern matching over much richer structures. So this is an F# record. So assume you have a watch that's generating this sensor events. What we can do is we can then map those sensor events into a structure like this. So you have a sensor of some type. Your ticks is a timestamp, and then XYZ values. So assume the watch is just giving us Android sensor data. We're converting that into this structure, and now we can do pattern matching in our state machines very easily. So here, for example, we're looking at, we're interested in linear acceleration sensor event, and we want to extract the Z value out of it and do something with it, right? So this gives you a very powerful way of building your state-to-state transition logic. Okay, so this is actual Android code that I'm showing here. I'm going to just show you how the gesture recognition kind of hooks in, with the state machine idea. So down below is an Android interface that we have to implement if we have to listen to sensor events. It's called iSensor Event Listener. It has two methods that we have to provide. The on accuracy change, we're not doing anything with that, but on sensor change event, we get this event, which is the sensor event. Here we're converting that into an F# record. So there's the sensor type, timestamp, and XYZ values. So it could be sort of, for example, linear acceleration, and these XYZ values would be acceleration at the different directions, relative to the watch. And what happens here is that we take this data, and essentially we have some current state in somewhere, and we evaluate this new sensor event against the current state, and this is the eval function over here, and we get the next state, and maybe an event was recognized, right? So what we do with the next state, we just store it in a mutable variable, and so the next state is a variable available when the next event comes in. And then if we recognize an event, we can then look at that and just process it, right? So this is now you can build your model your state machines any which way you want, using these kind of boiler, and then hook them in quite easily, using this kind of a pattern. So this is actual code that's running on the application. Okay. Now we're going to talk a little bit about how to handle complex patterns. So the thing is that we use the patterns we have looked at so far are still deterministic patterns, but now we want to get to gesture recognition, which is more complex probabilistic patterns. So the idea there is that let's say you're trying to recognize a swipe gesture. And swipe gesture means if you imagine the app on your the watch on your wrist, and you swipe in the Z direction, so you're interested mainly in the Z acceleration. You're interested to see if the Z acceleration exceeds some threshold, right? And then at that point, you might say, okay, well, if it exceeds that threshold, I might be in a swing phase, but I might not be. I'm not sure at this point, right? This could be just noisy data. So what you do is, if you exceed some threshold, then you switch to this another state where you were trying to see if you're in a possible swing phase or not. And here what you're doing is you're essentially, again, looking at the linear acceleration, but then you're just combining it with the previous Z value and calculating an average, right? So you're now accumulating the Z acceleration events and getting average Z acceleration over, and essentially you just looping into this state until you have enough data to make some kind of determination. Right, so if let's say you do it 30 times or so X number of times, and now you have enough confidence okay, I am in the swing phase or not. Now these events come in very fast, like in 20 milliseconds or so that you get a lot of events in a short period of time. And once you have enough data, then you can sort of switch over to the next pattern match clause to say whether you are in the swing phase or not, and then you can do subsequent processing, right? So the main idea here is that we can again use partial application, but this time combine it with aggregation, to start to handle probabilistic patterns, right? But we can go further, right? So let's say you're trying to recognize that swing gesture, but you don't know what the right value of this linear acceleration threshold is, right? It could be 5.0, could be 6.1. You don't know what the right value is. But what you can do is then say, okay, well, I'm going to parameterize my state machine by plugging in a configuration structure and then use values from that configuration structure. Now I can instantiate this state machine with different configurations and try out different values and make sure which one works best. By doing so, you've essentially created a way of training these state machines from data, or essentially making them machine learnable in terms of the parameters that are used. And again, you're using this partial application because you're partially applying this configuration to each one of your states and carrying it along. Okay, so in the interest of time, I'm going to just talk about, so this idea, actually, I've applied it in many different places, like I applied it on the watch, but one of the places I applied it was on Storm. Apache Storm is an event handling system. And so, you get thousands of events per second. Storm doesn't really give you any good way of building pattern recognition. You have to code that by hand. But I was able to put fsharp under Storm and use this mechanism to really, easily recognize patterns in real times. Okay, so that's what I'm going to do now is talk a little bit about how do you actually go about training or optimizing these pattern recognition systems using something like an evolutionary computing algorithm. Okay, so the process works as this. So first, what you do is, let's say you want to recognize some gestures. The first, what you will do is you will just perform those gestures X number of times and record the raw sensor output, right? So I actually had to build another app that just recorded raw sensor data and in a file, and then I transferred the file over to the phone. So once you have this raw sensor data, you can then start to look at, okay, well, as a human, you can then start to analyze this raw sensor data and come up with parameterized functional state machines to recognize these patterns. At this point, you don't know what the right value of these parameters are, but you know the general structure, you know the states and the transitions, but you don't know exactly when you want to transition and how much time you need to take to recognize a gesture or what the average value of some parameter should be before you make the transition. So those things you don't know at this point, but you have the kind of the general structure. And then what you do is you take that and create an optimization problem essentially, and so this involves a lot of details, so I won't have time to go into it, but I'll provide you references at the end of the talk. So you actually take this functional state machine with this parameterized this sort of parameterized functional state machines, and then you create a function based on these parameters to essentially the value of this function is maximum when your gesture recognition performance is best. So you recognize the gesture you're supposed to recognize. You don't recognize spurious gestures, and that's how you sort of construct this thing. So now you have your optimization function. You have your training data. You can sort of put it all together to say, okay, solve the optimization problem by running you're running your parameterized functional state machines on your training data. And what that really means is that the evolutionary computing algorithm will try out different values of these parameters and calculate the value of this fitness function till it finds a value that gives you the best results, right? So, and then that is where you've sort of used this data to find the parameter values that give you the best gesture recognition performance, given these parameterized functional state machines that you've created or modeled as a human. So you're combining sort of the human view, human modeling with machine learning. So it's a kind of what is known as blended intelligence. So it's a human does some of the work and the machine does a low-level optimization. And then at the end of the day, you have a better trade-off, right? So because you're involving the human and the machine to do parts of the work, you can then use these simple finite state machines, and you can get computational efficiency with them, and also get good recognition performance at runtime. Okay, I mean, this is the fitness function. I will not go through this. It's a lot of work. What I want to point out is that when I created this fitness function, I plugged in sort of my best guess values to see how will the gesture recognition work, and I got a score of -1.5. And after the optimization was done, I got a score of 92.5, and the maximum score I could get is 120. So this kind of shows that this is an effective technique. What I want to show you is that when you're creating this is what the parameters look like, right? So you have about 40 or 50 of these parameters that get used in your state machines. And after optimization, you find the right value of these parameters. These parameters are things like thresholds and limits and tolerances, right? Those are kind of things that inside the state machine. Essentially, these get used for transition decisions. Okay, just a brief overview of, there are many evolutionary computing algorithms out there that you can use to solve such a problem, like genetic algorithms is the most commonly known one. There are many others. I happen to be working on this particular area, cultural algorithms. That's part of my sort of PhD work. So that's the one that I used, but you can use any number of them. I'm going to skip through that. I'm going to show you that this is kind of a track of the evolutionary computing algorithm working and trying to, improving the score using the fitness function score by finding better and better parameter values. Just a chart to show you that. Okay, so now I can summarize. So what we talked about is a way of using functional programming for modeling state machines, and then once we do it that way, we have much more capability to handle more complex patterns, using this idea of, partial application, but then we can even take it further for recognizing stochastic patterns through machine learning. And I just want to point out that F# is a great language, and it's a great language for implementing a concept like this. Works well on small devices like watches, but in the future, Google is coming up with this Brillo platform, and hopefully, if Mono works on that or Xamarin works on that, you'll be able to deploy a code like this on your internet devices.
Awesome. This is good stuff. And so we're almost out of time, but I wanted to ask a couple of questions. The first one is it becomes clear to me that first what you're doing is you're getting a lot of training data. You're looking at the training data to find out what the state machine could be. Then you're guessing parameters and you're optimizing over those parameters for that structure, right? Is that correct?
Yes, that's exactly right. So we're basically collecting a lot of data, and then as a human, we're coming up with these state machines, but
right.
These are rough kind of state machines, and they
Sure.
have a lot of parameters whose values we don't know.
Correct.
And then we find those values using this kind of approach.
So what wasn't clear to me was for each of those state machines, are you looking at one gesture at a time for each of the state machines?
Yes, there's one gesture at a time, but the fitness function puts all of these together into one group, and the value is calculated over the entire set.
I see. So then the fitness function, what it's doing is it's measuring over the pre-computed structure, the human computed structure based upon the data analysis. It's finding the optimal fit given the parameters. Is that right?
Exactly.
Is this a convex function, non-convex function? How do you know you've arrived at the best optima?
Yeah, so we don't know. This is not a numerically, it's not a numeric problem. These are state machines, discontinuous. We don't even know what the landscape looks like. So
right.
That's why an evolutionary computing algorithm is suitable, because it uses stochastic search and tries out different solutions and does kind of hill climbing in its own way.
This is awesome stuff. Where can people go to find out more about your work?
So in the references, there's a couple of papers that were published. They can actually look at the code that's out there. On GitHub, there's the actual code that you can get for the watch. It's not for the training application, the work, but these papers sort of explain, the concept in more detail.
Awesome. Well, we are out of time. Thanks so much for spending some time with us. It's been great, really informative, seeing how you could use machine learning for gestures on a watch and a phone. Thanks so much, my friend.
Thank you.
All right, we're going to go to Slate so we can get our next guest in. We'll see you after the break.